Hello students, how are you? I think you are all well. Today I am going to teach you nucleophilic substitution at saturated carbon. This is very important and it is like must learn thing in reaction mechanism. If you want to learn the reaction mechanism, then first you need to have a good concept on nucleophilic substitution at saturated carbon. The classical example of a nucleophilic substitution at saturated carbon is the conversion of an alkyl halide to alcohol by the treatment of aqueous alkali. What is this? It means Rx, aqueous alkali, gives alcohol ROH, and this group gets leaves from the Rx, X minus. This is a classical example of nucleophilic substitution at saturated carbon. As R is CH3, I am considering R is a alkyl group, then obviously it is saturated carbon. So example is very simple, and much of the understanding regarding the mechanism of this kind of reaction was revealed by two great scientists, Sir Christopher Ingold and Edward David, in England in 1930s. Now let us try to consider the following reaction. H3C beer, like methyl bromide, aqueous alkali. You can consider aqueous potassium hydroxide or aqueous sodium hydroxide. Okay, then we are getting methanol and Br minus. Clear? Here the rate law is found to be rate equation. Calculated rate equation is rate constant, concentration of CH3Br, and concentration of alkali. Here only hydroxide ion takes part in the reaction. That is why I am considering the concentration of hydroxide ion. Clear? So now it is clear that the power of concentration of CH3Br is 1, and for HO minus it is 1. So order of the reaction is 1 plus 1, that is 2. Is that clear? So you can say this reaction follows second order kinetics. This reaction follows second order kinetics. Who are in class 12, I think they know chemical kinetics. Okay, try to remind the concepts of chemical kinetics, how to evaluate the order of the reaction. Okay, if I give you a balanced chemical reaction, or if I give you a elementary reaction, I think from the stoichiometric coefficient you are able to calculate the order of the reaction, which is very easy. Clear? That I am not going to explain now. So up to this study, we can say that this reaction follows second order kinetics. To explain this, it has been suggested that both the molecules CH3Br, that is methyl bromide, and HO minus alkali are involved in the rate determining step. Clear? Which is rate determining step? The slowest step is the rate determining step. Clear? But here the reaction is only single step reaction, and that is why, so as it is single step reaction, that is why first I am giving you this example, because it is the easiest one. So first try to learn single step reaction, then learn multi-step reaction. That is why this kind of reaction is very important in learning or organic reaction mechanism. Clear? So both the molecules CH3Br and HO minus are involved in the rate determining step, that is RDS. This CH3Br and alkali HO minus both are involved in rate determining step. Clear? Now, if I show you the mechanism, then it becomes, so it is the CH prime is representation of CH3Br, HO minus, bromine is electronegative, so you need to put a positive charge on carbon. Clear? On carbon. So, and delta negative on bromine. Clear? So HO minus, obviously HO minus attacks delta positive charged carbon. When it attacks the delta positive charged carbon, then interaction between carbon and hydroxyl ion makes carbon pentavalent, which is not possible. So one group must be left from the system, that is Br. Clear? And this like bonding between carbon and oxygen, and bond making between carbon and oxygen, and bond breaking between carbon and bromine happen simultaneously. That is very important thing. Okay. So in the transition state, bond between oxygen and carbon is about to form, and bond between carbon and bromine is about to break. Clear? This is the geometry of transition state. Now, in the product, CBr bond completely breaks. So we'll have this product. We'll get this product. One thing is very important. Try to concentrate on configuration of carbon. Here, the configuration of carbon gets inverted. So inversion happens this kind of reaction. Inversion at halogen bearing carbon, right? And during this reaction, the part of energy necessary to affect the breaking of CBr bond, because CBr bond breaks and HOC bond is formed. Clear? So thus the part of the energy necessary to affect the breaking of the CBr bond is supplied by the energy that is produced in the formation of HOC bond. Clear? When bond is forming, then energy is liberating. Energy liberates. When bond forms, then that time energy liberates. Okay. When bond breaks, that time energy is required. Clear? So in the transition state, first this carbon is sp3. In product, it is also sp3. But in transition state, see, in transition state, it is sp2 carbon. Clear? So sp3 hybridized carbon atom in the reactant becomes sp2 hybridized in transition state. Clear? And the HO and Br being associated with the lobes of the unhybridized p orbital, that is thereby made available on the central carbon atom, because you know that sp2 hybridized carbon has one unhybridized p orbital, and here I am saying that the HO and bromine being associated with the lobes of the unhybridized p orbital, that is thereby made available on the central carbon atom. How it looks like. Now I am going to show you the bonding pattern of transition state. Clear? So this is anhydrous p orbital. Okay. Is that clear now? I think it is clear. And this type of mechanism has been designated by C.K. Ingold as Sn2. This kind of reaction is called Sn2 mechanism, Sn2 reaction. A stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. Because in the transition state, 2 molecules are involved, so it is bimolecular. Very simple. And the energy profile diagram for this reaction is this one. Energy in y-axis, this is reaction coordinate, reactant, product. It's single step reaction. In single step reaction, the number of transition state is 1. In two step reaction, number of transition state is 2 and there will be 1 intermediate. That I am going to explain after some times. Okay. So this is the transition state. This is product. This is reactant. Clear? And another important thing, just I am giving you a comment that see, hydroxyl ion attacks from the backside. Is there any concrete reason behind this? Yes, there is a very concrete reason. So I can explain you why hydroxyl ion attacks from the backside. Okay, that can be explained from the molecular orbital concept from molecular orbital theory. But right now I am not going to explain those stuff because at this level this is beyond my scope, because you were in class 11, 12 or first year. But that is why I am not going to explain this thing. So if you have any queries, then you can contact me. Okay, I already have given my contact details in my YouTube page. Okay, so then I can explain you why backside attacks is preferred in Sn2 reaction. Clear? Let us consider another type of nucleophilic reaction. Okay, I am giving you the example. Here, this is tertiary alkyl halide. Okay, and I am treating this tertiary alkyl halide with aqueous alkali, means aqueous sodium hydroxide or aqueous potassium hydroxide. Okay, then product is this one, tertiary alcohol and Cl minus. Is that clear? Here the rate law is found to be K, just concentration of tertiary alkyl halide. So here rate is independent of concentration of aqueous alkali. That is very important thing. Why? So that is the reaction is independent of the concentration of alkali. So reaction doesn't depend on the concentration of alkali. Concentration of alkali. I am using the third bracket to for concentration. Okay. So that is the reaction is independent of the concentration of alkali and reaction follows first order kinetics. Yes, power is 1, so order is 1. So reaction follows first order kinetics. That is very important. First order kinetics. This reaction follows first order kinetics. Clear? To explain this, it has been suggested that tertiary butyl chloride ionizes slowly to form an ion pair in the rate determining step. So this ionization process, like when that is tertiary butyl chloride ionizes slowly to form an ion pair in the rate determining step. So this is the rate determining step. Okay, so I am showing you. This is tertiary butyl chloride. Clear? Chlorine leaves from the system. So if chlorine leaves from the system by taking up the bonded electron pair, then what will be the product? What will be the intermediate? What will be the product? What will you will get? Carbocation. Very simple. So already I showed you the formation of carbocation. Just see my previous video, reaction intermediate. Okay. So this is the carbocation plus and Cl minus. So that is why I am telling you this is the step for the formation of ion pair. So this is the rate determining step, RDS. Okay. Now you have an aqueous alkali. So now HO minus can attack. First process, this step is very fast. Or H2 can attack, because aqueous alkali means water is present. Solution of alkali in water, right? So either water or HO minus can attack the carbocation. Then what you will get? Or okay, then you will get the, if HO minus attacks, then directly you will get the corresponding alcohol. Okay, and that is very important. So this HO minus or H2 can attack either side of the carbocation. Means carbocation is planar. Okay, it can attack from the bottom or it can attack from the top. Okay, it leads to a very unique phenomena. Okay, that I am going to discuss after some time. That is called racemization. Obviously I will explain this racemization process, but okay. But now what happens if water attacks? Then what happens if water attacks? H2 plus, because now when water makes bond with carbon, then number of bond arising from oxygen becomes 3. That is why you need to put a positive charge on oxygen atom. So now departure of one proton gives you this product. Clear? So final product is alcohol, tertiary butyl alcohol. The energy required for the formation of ion pair is mostly recovered from the energy evolved through the solvation of the ion pair. Solvation process is exothermics, energy liberating process, and that energy is being used to used for the formation of ion pair. Okay, that is very important concept. Clear? So now I am telling you the I'm uh, showing you the energy profile. Okay, so this is reactant, so this is product, energy, reaction coordinate, the first transitions, the first transition state. This is the intermediate. Here intermediate is carbocation. Mind it, intermediate is carbocation or ion pair. Means carbocation plus the leaving group. As well, this is ion pair. Okay. Next transition state. When alkali or water molecule makes bonds with carbon. Makes bond with carbon of the carbocation. Central atom, that is carbon. Okay. This is transition state 1. This is transition state 2. So it is clear that if two-step process, then number of transition state will be 2 and there will be one intermediate. Clear? Okay. So I told you that this carbocation is planar. Already in reaction intermediates, in the videos of reaction intermediate, I already told you that carbocation is planar structure. Okay, so if you have if 3R group are different, R1, R2, R3. Okay, this is Cl aqueous alkali. Then what will be the product? You can think, okay, product will be very simple. Tertiary alcohol. But then you are thinking that all the 4 groups attached at the central carbon are different, so reactant and products both are optically active, means carbons should be chiral. Okay, when now 4 groups attached at the carbon, if those are all different, then that compound should be optically active. Okay, means it can rotate the plane of polarized light. So obviously I will discuss what do you mean, what is plane polarized light, everything I will discuss in the separate video. Just who knows what is chiral carbon, for them it should be clear. Okay, so at a first glance it looks that reactant and product both are optically active, but actually not. You will get optically inactive product. Why? Now I am going to explain. Intermediate is carbocation. So intermediate is carbocation, and which is planar. Now the nucleophile, here it is HO. Suppose I am considering HO minus. So HO minus can attack from top, either from the top or bottom, because it is planar structure. Then yes, you will get this one. So beside this plus, obviously you will get this tertiary alcohol, but additionally you will get this alcohol also. And what is the relation between these two alcohol? That is the mirror image. These two are mirror image with each other, and the as probability of attack of HO minus from the top and probability of HO minus, probability of attack of HO minus to the carbocation from the bottom, both will be same. Both probabilities are same. That is 50-50. So concentration of these two products are 50-50. So each this product, this one and this one, both are optically active. Both are optically active. But as they are mirror, these two are mirror image with each other, then if this one rotates the plane of polarized light by plus x degree, then this one will rotate the plane of polarized light by minus x degree. Then as a whole, there will be zero optical rotation. But each molecule is optically active, but mixture is optically inactive. So this is called receiving mixture. Racemic mixture means 50-50 mixture of enantiomeric pair. So they are enantiomer, and I will discuss the proper definition. I obviously I will tell you the proper complete definition of enantiomer, but right now I am telling you that these two are enantiomeric pair. Okay, clear? So this is racemic mixture. Racemic mixture is the 50% mixture of two enantiomeric pair. Clear? So here, right now I am trying to summarize this kind of reaction. See, this reaction follows first order kinetics. So it depends only concentration of alkyl halide. Okay, so it is again, so Cl group gets substituted by HO minus. Okay, Cl group substituted by HO minus. Okay. So it's a substitution reaction, and here reaction proceeds through the formation of carbocation. So here this carbon center is electrophilic, so it is attracted towards electron rich species, and electron rich species is HO minus or H2, because in H2 oxygen contains two lone pair, so potentially it is a negative charged species. Okay, so HO minus and H2 behaves as a nucleophile, means it is attracted towards positively charged species. Nucleophile means nucleo means positive and phile means love or attraction. So oxygen or HO minus and H2 behaves as a nucleophile, and this carbon behaves as a electrophilic center. So that is why this reaction is called Sn1 reaction. This is Sn1 reaction. S stands for substitution, N stands for nucleophile, and 1 stands for unimolecular. Because reaction, this rate of this reaction depends only on concentration of alkyl halide. So in the rate determining step, only one molecule is involved. So that is why it is unimolecular reaction. So clear? So this is Sn1 reaction. This kind of reaction is Sn1. And previous example, in the previous example, I have shown you Sn2 reaction, because in that reaction rate depends on two species, alkyl halide and alkali. Okay, and nucleophile. When alkali behaves, HO minus behaves as a nucleophile. Here, okay, here also HO minus behaves as a nucleophile, but HO minus or H2 doesn't involve in the rate determining step. Okay, because this step is very fast, and we know that slowest step is the rate determining step. Clear? So now we'll check how, we'll see how structure of substrate influence on the reaction kinetics, this substitution reaction kinetics of this substitution reaction. Clear? Effect of the structure of substrate on substitution reaction. Now let us consider the treatment of aqueous sodium hydroxide solution on the following series of compounds. First one is CH3 beer, methyl bromide. Second one is CH3 CH2 beer. Clear? So this is ethyl bromide. Next one is secondary alkyl halide, alkyl bromide, and the fourth one is tertiary alkyl bromide. So it is tertiary butyl bromide. Clear? So now the first, we have the following observation. The first, this is the first one, and the last member, first and last member, this, so CH3 beer, that CH3 beer, and this one, tertiary butyl bromide, it undergo weak hydrolysis. Right now I am not telling which whether which one which one is involved in Sn1 or which one is involved in Sn2. That I am not going to say. Okay, but observation is these two species, these two substrates undergo weak hydrolysis. Clear? And there is a changeover in the order of the reaction on moving left to right. On moving left to right, there is a changeover in the order of the reaction. This CH3 beer and CH3 CH2 beer, it follow second order kinetics. Means it follows Sn2 reaction. Okay, and the last member means tertiary butyl bromide, it follows first order kinetics. Clear? This is the last member, it follows the first order kinetics, this one. Clear? And this one, the third one, secondary alkyl bromide, that means this one, it follows mixed kinetics. Clear? Means it follows mixed kinetics. At higher concentration of alkali, here it is in sodium hydroxide, it follows second order kinetics, means it follows Sn2, and at lower concentration of alkali, it follows first order kinetics, that is Sn1, it follows Sn1 reaction. Now we need to give you, I need to give you a proper explanation, because I need to give you proper explanation for this observation. Okay, so in seeking an explanation for the observed changeover in the mechanistic pathway, we need to consider in each case the effect of both electronic and steric factor on the transition state. Okay, that is very important. So on moving left to right, the electrophilicity of the carbon bearing halogen, means this carbon, electrophilicity of carbon bearing halogen, electrophilicity of the carbon bearing halogen decreases because of the enhanced plus I effect on the increasing number of methyl groups. See, in this substrate, there is no methyl group is attached to this carbon, but here one. Here two methyl groups is attached to the halogen bearing carbon, means bromine bearing carbon. Here three methyl groups are attached to this bromine bearing carbon atom. We know methyl group CH3 group has plus I effect, means electron donating effect through sigma bond. Electron donating effect through sigma bond. So what I am telling you, that on moving from left to right, the electrophilicity of the carbon bearing halogen decreases because the enhanced plus I effect of an increasing number of methyl groups. As number of methyl group increases on moving left to right, then actually methyl group donates electron density through sigma bond. So the electropositive S halogen bearing carbon atom has delta positive charge. Clear? But this delta positive charge density decreases. Why? Because on moving left to right, number of methyl groups attached to the halogen bearing carbon atom increases. Clear? So that is why the on moving left to right, I can tell you that extent of delta positive charge on halogen bearing carbon atom decreases. Clear? So the nucleophile, here it is HO minus. So HO minus should have a lower tendency to attack the carbon bearing halogen atom, because HO minus loves to attack the carbon having high positive charge density. But in the extreme right, the positive charge density on the halogen bromine bearing carbon atom is the lowest one. Clear? I think it is clear. So thus Sn2 becomes increasingly less favorable on moving left to right. I think it is clear now. So now during Sn2 reaction, the transition state becomes relatively more crowded. Just try to remember the geometry of transition state in the Sn2 reaction, which is pentacoordinated. This is the geometry of transition state in the Sn2 reaction. Clear? So it is pentacoordinated. So in each case it will be pentacoordinated. So means pentacoordinate carbon with the 5 substrate. 1, 2, 3, 4, 5. Okay. Compared to that of reactant is tetrahedral. Okay, means tetracoordinated carbon with 4 substituent. In each case 1, 2, 3, 4. This halogen bearing carbon has 4 substituent. That is why on moving from left to right in the above series, the relative crowding increases. because here number of methyl group is 0, number of methyl group attached to the halogen bearing carbon. Here it is 1, 2, in this case it is 3. So methyl groups exerts a steric effect. Okay, means when there are 3 methyl groups, then the pentacoordinated transition state will have higher energy due to steric effect. Clear? So like I think it is very easy. Like 3 big substituent, actually here 3 1 2 3 4 5 out of 5, 3 there are 3 substituents are larger in size, so there will be a van der Waals interaction. I mean, steric it means van der Waals interaction means it's a kind of steric interaction. Steric interaction kind of a van der Waals repulsion, means it exerts van der Waals repulsion. Origin of steric effect is the van der Waals repulsion. This is the origin. Clear? Origin of steric effect is the van der Waals repulsion. So due to steric effect, the energy of transition state in this case, in the extreme right, this tertiary butyl bromide, energy of transition state will be high. So if energy of transition when energy of transition state increases, then reacts, then activation energy will also increase. See, this is reactant, this is product. When see, this is the transition state for 1. Okay, and this is substrate. So this is substrate 4, and here this is the transition state. See, activation energy is very high. So higher activation energy means lower will be the tendency. Lower will be the tendency to carry out the reaction. So reaction will not proceed easily because it requires high energy. So this is the barrier. So energy barrier is very high. This is the transition state for 4, TS4. It is TS1. Clear? I think it is clear now. So again I am telling you, during Sn2 reaction, the transition state becomes relatively more crowded. Yes, substrate is tetracoordinate, transition state is pentacoordinated. Okay. So on moving from left to right, in the above this in this series, the relative crowding increases because here number of methyl groups attached to this halogen attached to this bromine bearing carbon is 0. Here it is 1 methyl group. Here 2 methyl groups. In the tertiary butyl bromide, 3 methyl groups. Clear? So it exerts steric effect. So on moving left to right, Sn2 becomes less favorable. Reason? Steric effect. Coming from methyl groups. Clear? Now on moving from left to right, the stability of the carbocation formed becomes progressively greater through plus I effect and hyperconjugation of increasing number of methyl groups. See, the corresponding cation, in this case CH3 plus, here it is this is 2 degree carbocation. Three degree carbocation. So this The stability of carbocation increases due to plus I effect of methyl groups, 3 methyl groups, 2 methyl groups, 1 methyl group, 0 methyl groups, and hyperconjugative hydrogen, hyperconjugation. Here number of hyperconjugative hydrogen is 9, here 6, here 3, in this case 0. So the stability of carbocation increases on moving left to right, on moving from left to right. So that is why we know Sn1 reaction involves formation of carbocation. Sn1 reactions proceeds through the carbocation, and so that is why Sn1 is expected to be more favorable on moving from left to right. So concept is same. If the intermediate, here carbocation is the intermediate, okay, if when intermediates get stabilized, then transition state also becomes stabilized. When transition state becomes stabilized, then activation energy will be less. Clear? Now I am explaining. This is the energy profile for the Sn1 reaction. This is reactant, product. First, this is intermediate. Here it is carbocation. This is carbocation. The second, now product. This is transition state 2. This is transition state 1. Now, if intermediate carbocation gets stabilized, then transition state also becomes stabilized. Then activation energy, now required activation energy becomes small. Okay, so reaction proceeds very easily. Because energy barrier gets decreased. If energy barrier gets decreased, then reactions proceed smoothly. Okay, so that is why in case of tertiary butyl bromide, Sn1 is preferred one. I am going to give you examples of two substrates which are resistant, two types of substrate which are resistant towards nucleophilic substitution. These two kind of substrates are, first one is vinyl halide. Here it is vinyl chloride. This system, just remind and just try to memorize that this is vinyl system, vinyl chloride. Like C-double-bond-C, this is called vinyl system. And another one is chlorobenzene. Okay, note carefully that in this substrate the carbon bearing the halogen is an unsaturated. So this is unsaturated because hybridization of this carbon is sp2. And the lack of reactivity can be explained by considering the following facts. First one is that here the carbon bearing the halogen atom is sp2. This carbon is sp2 hybridized, and this carbon is also sp2 hybridized. Thus, but in case of alkyl halides, it is sp3 hybridized. Like suppose CH3, CH2X, or it is sp3 hybridized. Okay, here it is sp2, but in case of alkyl halides, it is sp3 hybridized. Thus, in vinyl halides and in aryl halides, the carbon halogen bond is stronger. CsP2X bond is stronger than that of CsP3X. Okay, this is stronger than CsP2X bond is stronger than that of CsP3X. Why? Because CsP2X. So this kind of bond involves in conjugation. Okay, suppose this is vinyl chloride. Just see, CX bond gets some double bond character through this resonance. This is true for chlorobenzene. This is true for chlorobenzene also. See, this CCl bond gets some double bond character. Thus, carbon-chlorine bond has partial double bond character. Here it is single bond, here it is double bond. See, in this canonical, CCl bond is single, but here it is double bond. CCl bond is has double bond. It is the CCl bond is double bond. Okay, so as a whole, that is why I am telling you that thus the carbon-chlorine bond, this CCl bond gets double bond character. Clear? So that is why in case of alkyl halide, whereas in case of alkyl halide CCX bond is pure sp single bond, here it is, this bond is pure single bond. But in case of vinyl halide or in case of aryl halide, CCl bond gets some double bond character. So in vinyl and aryl halide, the carbon halogen bond is difficult to break. So it is difficult to break. If CCl bond is difficult to break, then nucleophilic substitution, that is why it is to some extent resistant towards nucleophilic substitution, because in nucleophilic substitution, CCl bond means carbon leaving group bond breaks, but here breaking needs more energy because CCl bond or carbon nucleophile carbon leaving group bond is stronger than that of alkyl halide. Clear? Next reason is the pi electrons. The pi electrons of double bond in vinyl halides and in aryl halides are also inhibit the close approach of an attacking nucleophile. Try to understand. This is the pi cloud. Now we know that this is the pi cloud. We know that nucleophile attacks from backside. If it attacks from backside, then nucleophile is negatively charged and pi cloud is also electron rich, right? So there will be repulsion between nucleophile and pi cloud. Clear? So that is why the approach of an attacking nucleophile gets inhibited by the pi cloud. Clear? I think it is clear. Next point is, for Sn2 reaction, the attacking nucleophile must approach the vinyl halide from the backside of the halogen bearing carbon and in the plane of the alkene. Obviously, this leads to a steric interaction between the nucleophile and the substituent on beta carbon. Here beta carbon, this is the beta carbon. This is the beta carbon. Okay. When nucleophile tries to attack from backside, then there will be a steric interaction with this group. Clear? Again, if you consider, okay, fine, Sn1 may happen, but Sn1 reaction, the Sn1 reaction proceeds through the formation of carbocation. But here vinyl carbocation or aryl carbocation are highly unstable. there is no stability. Clear? This carbocation or this aryl carbocation has no stability. Aryl carbocation, or here it is phenyl carbocation. It has no stability. So any aryl carbocation which needs linearity at the carbon bearing the positively charged is impossible to attain. Thus, Sn1 is most unlikely. Is that clear? First one is it is very unstable. These two types of carbocation is very unstable. Then if carbocation is unstable, then reaction will not proceed through carbocation. Then there will be formation of carbocation gets not formation of carbocation is not preferred process. So then Sn1 is most unlikely to happen. Clear? So considering following points, I can say that it is true that the direct Sn2 reaction usually do not take place on alkynyl substrate, but on very rare occasion. Okay, Sn2 reaction most unlikely to happen in case of aryl or vinyl halides, but in rare occasion, Sn in very rare occasion, very rare, Sn1 reaction may occur, which may happen, okay, but which needs, but if Sn1 reaction sometimes it may happen, but if and only it must contain a super good leaving group like N2 plus. Okay, if this is very important, if leaving group is very good, super leaving group, then Sn1 may happen. Okay, in aryl or phenyl halide. Clear? And there may be another point, there's may be present an electron donating or cation stabilizing group at alpha carbon which stabilizes the incipient, which stabilize the vinyl carbocation by resonance. Okay, so another point is that leaving, okay fine, revealing group must be very good. Beside this, additionally, there should be a electron donating or cation stabilizing group at alpha carbon, so that it somehow it can stabilize the carbocation, because vinyl carbocation, aryl carbocation is very unstable. Okay, so so I can summarize that Sn2 reaction usually do not take place on vinyl or aryl halide, but in rare occasion Sn1 reaction may happen in vinyl or aryl halide. Okay, but there are some condition. First condition is leaving group should be very good leaving group, and there should have carbocation or stabilizing group. Then Sn1 reaction may happen. Okay, I will give you examples in my next video. In next video, I will discuss nucleophilicity and nucleophilicity, living group criteria, about living group, and also I will give you some examples of Sn1 and Sn2 reactions. Okay, because in some condition reaction proceeds through Sn2, but in some cases if you change the condition, then that reaction proceeds through Sn1. Okay, bye.